Hello and welcome. Today we will go through the slides on decision diagrams and the AdLib framework. In this first presentation we will focus primarily on decision diagrams. So what are decision diagrams? Decision diagrams are a data structure constructed from a decision tree. They just more compactly represent the Boolean function or algebraic function or set function that the decision tree was trying to represent. It is a data structure that is rooted. You can see the root of email urgent, directed in that it only goes from top to bottom, and it is an acyclic graph, so there are no cycles within the decision diagram, so known as a DAG structure. They have decision nodes. They have a high pointer, so that's when a decision is true, such as here, subject contains earning. True, we go to subject contains newsletter, and this is represented by a solid line. It has a low pointer. This is when the decision is false. So subject contains urgent false goes subject contains deadline. And this is represented by a broken line. And it also has terminal nodes. So these are the true or false at the bottom. These can be changed for let's say this is for a Boolean decision diagram. If you want an algebraic decision diagram, these will be 0.0, 0.1 up to infinity. So they represent real numbers, or they can represent integer numbers, etc., depending on the type of decision diagram you're trying to represent. So you start with the root, you go down to a decision node. It essentially is a predicate, so it's either true or false. True, you get the high pointer, represented by the solid line. False, represented by the low pointer, which is a broken line. And this moves all the way down, moving from top to bottom, terminating at a terminal. The key concepts of decision diagram is that they are ordered. A fixed variable ordering must be reserved. Say you start here with x1 and you go down to x2 and then to x3. That order must now be preserved throughout the decision diagram. So say this is the high pointer, so true and true. The low pointer cannot point to x3 and then down to x2. This is invalid. You must preserve the ordering. So this must be the same as the other side. So this must also go to x2 and then to x3. Or this can go directly down to x3 if x2 is not needed. But the ordering must be preserved. So x1 first, x2 if in the next position, and then x3. Next, decision diagrams are reduced. So all redundancies are moved from decision diagrams. Primarily consists of 3 steps. So merging the equivalent leaves, merging isometric nodes, and eliminating redundant tests. So as you are creating a compact representation of Boolean functions and removing all unnecessary nodes from your decision tree to make it as compact as possible. Finally, decision diagrams are canonical. This means there is only one single representation for a decision diagram. So if you gave the Boolean function to 5 different people, you told them to build a decision diagram, each 5 person will come up with the exact same representation. That's simply what canonical means. There is no other representation for that specific decision diagram when compressed. Continuing on, the if-then-else operation is how you move in decision diagrams. The if represents the predicate in which you are currently positioned. Then would represent whether the predicate was true, which would be the high pointer. You would move down the then branch. And if the predicate was false, you'd move down the else branch or the low pointer. Applications of decision diagrams, as we mentioned previously, is that compactly represent Boolean, algebraic, or set functions. These are to represent classifiers, regressors more compactly. The main aim of reducing the amount of memory required and the amount of time it takes per classification. Another application for decision diagrams is equivalence checking. This is based on the canonicity of the decision diagrams, and this is to determine whether 2 functions, be it Boolean, algebraic, or set, are the same. This is done based on whether the variable ordering of the decision diagrams is equivalent. Next, we move on to binary decision diagrams. So these compactly represent Boolean functions. So this would have true or false terminals, and it has a root going down to a predicate, and true, solid line down, false, broken line to the low pointer. It has a Boolean domain and goes to a Boolean codomain. So that just means we're staying with true and false as our terminals. Operators are and, or not. Move on to algebraic decision diagrams. Again, very similar to binary decision diagrams. However, we now compactly represent algebraic functions. So we're now going from Booleans to reals. So now our terminals, as you can see, are 0.2, 0.6, 1.0, and vice versa, any value, any real value. So we're no longer doing true or false for our terminal values. However, we're still using the if, then, else operations within the trees. So again, we still have our predicate. If it's true, then take the high pointer. If it's false, then take the low pointer. Operators now are plus, minus, multiply, divide, max, min. Because we're dealing with real values, we can now use mathematical operations as opposed to Boolean operations. Our terminals are now n-ary. You can have multiple terminals. You can have more than 3. You can have 4. You can have 5. And the values can go from minus infinity to plus infinity in real values. So binary decision diagrams construction. You start off with your truth table. So let's say we're given 3 variables, x1, x2, and x3. So we have 3 variables. We're going to have 8 values. So 0, 0, 1, 0, 1, 0. Let's say the result of this binary function is 3 zeros gives you a 1. This gives you a 0, 0, 1, 0, 0, 1, 1. For our truth table, we have to represent this as a binary decision tree. So again, we have our 3 variables, and again, 2 to the power of 3 means there are 8 different options. It's represented here by the truth table. So in our decision tree, we're going to need 2 to the power 3 minus 1, which equals 7 nodes. So again, every decision diagram has to have a root. So we're going to start with x1, go down to x2, and your root would be f. So that could just be the function that we're trying to represent. And that will go down to x1. x1 will go down to x2. So if true, we'll go down to x2. False, go down to the other x2. And again, x2 would have the same thing. So down to x3 for true, x3 for false, x3 for true, and x3 for false. So represent each binary decision. And this is our output we were looking for. So we were looking for a 1, 0. So that would be true, false. 0, 1, false, true. 0, 0, that'd be false, false, and true, 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 true. So this is what we were trying to represent. So what gets true in the first position? So it's 0, 0, 0. So they would all be false. This would have to be a broken line that represents else or not x1. It's also not x2, 0. And it's also not x3. I think I should have used a different color. In fact, I will go back and use a different color. So what gets you 0? That's 0, 0, 1. So false, false, except x3 is now true. So this is a solid line which goes to false. To get our third 0, it's 0, 1, 0. So 0, x1 is false, x2 is true, going to x3, and then x3 is false. So broken line. Next one again, x2 is true, x3 is true, so solid line to true. And now we're on the other side, the second part, or second 4. So you can almost draw a line here. So when x1 is true, x2 is false, and x3 is false, gets 0. So when x1 is true, x2 is false, x3 is true, it also brings you false, so this goes to false. Then we go to x2 is true, and x3 is false, goes to true, and when it's true, it also goes to true. Now we have our decision tree. So the next thing we have to do is create a binary decision diagram. I'm going to represent Boolean function 100, 100, 11. When x2 and x3, you could just easily have is email urgent, etc. Is x2 can represent is it a newsletter, x3 can represent is it from a shop, etc. So these variables are basically the predicates. So instead of using is email urgent, I'm using x1, x2, x3, but it's all the same underneath. That is it for this set of slides. In our next lecture, we will go to reduced ordered binary decision diagrams. Thank you.